Our next higher order function is map. This is probably the higher order function I use the most. I use it in all kinds of languages, not just functional programming languages. It's just such an important concept. I use it all the time. Okay, let's take a look at its type and what it does. We'll play around with it a bit, and then we'll look at some variations on it. So, given implicit types x and y, we take a function x arrow y and a list of x's, and we'll return a list of y's. What do? Well, if the list is empty, we just return the empty list. Otherwise, if we have a head and a tail, if we find a cons in our list, we'll apply the function to the head and then keep going on the tail. So we're just going to pointwise, is the technical term, pointwise apply f to every element of the list, sort of working our way from the front to the back, building a new list. So let's look at some examples to see what goes on. So here we're mapping the function plus 3x on the list 202. We get 535. 3 got added to everything. Now, if you remember how partial application works, we can write this a little more succinctly. Right? And this to me is very nice. Like we talked about concision when looking at filter, and this again is like such a clear and concise phrasing of this idea. It's worth for these examples and for the filter example prior to think, how would you write this in the language you already knew? Does that language have filter? If it does have filter, do people use it all the time? Or is it kind of a rare feature to use? Worth knowing. In any case, having the idea of filter and map in your head lets you quickly sort of have idioms for problems you need to solve. And I think in many ways, programming as craft, the ability to choose a good idiom is sort of what makes it easy to solve hard problems. Now, in this example up here, the types x and y are the same. We're taking a list of nats and we're getting back out a list of nats. But it doesn't have to be that way. Here we're going to take a list of nats and we're going to get a list of booleans where the boolean says whether or not the number was odd. Now, you can of course also do this with compound types. You can go crazy. Here we're going to turn a list of lists of booleans where the first one says, hey, was the number even? And the second one says, was the number odd? So it'll either be true, false, or false, true, or we have a bug in odd and even. So map happily accepts that too. And this is where polymorphism plays really nice. So polymorphism and higher order functions and anonymous functions are all playing together really nicely here for us to very succinctly write a fairly complicated program. Pretty cool. Okay, let's talk a little bit about map's type. So here's the definition of map. Just keep it on the screen. What type does map have? Think about it for a second. So multiple choice problems just beg for process of elimination solving. So here, this can't be it. What happened to y? What are you talking about? There's a y here, there's a y here, there's a y here. You can't just leave stuff out, Prof. Greenberg. It's not nice. This one, we can bounce immediately. So it's down to maybe one of these three. All right, so let's sort of compare. So this one and this one are pretty similar. They just have the for all xy there. This has the for all xy rather, and this one doesn't. But then the rest is the same: x arrow y, arrow list x, arrow list y, after a for all or not. And then this one puts parentheses around the arrow. So we have to decide: do we get a for all or not? And I guess it's kind of a question because these are implicit arguments. Maybe yes, maybe no. Let's say yes. Right, that we do. So that rules this one out. So now it's between number 1 and number 3. So it's really about this parenthesization, and that's a question about higher order functions. Now recall how currying works. X arrow y arrow list x arrow list y means a function of this type has given two types x and y. First takes a value of type x, then takes a value of type y, then takes a list of x's and returns a list of y's. But wait a minute, that's not what map does. It doesn't take values of type x and y. It just takes the one list. It takes a function f of type x arrow y. Okay, the function arrow is right associative. So if you're writing a type that has a function arrow in it, it's going to need to have parens unless it's going somewhere on the right. So number 3 is the right answer. And we can see that if we check at map. Now, if we check just map, it's a little confusing, right? We get these funny variables, question mark x, question mark y, that are used for Cox type argument synthesis. And I would still say that this still has the for all type, even though we're not seeing it. The check at map maybe gives us the clearest one. Okay, couple of variations. So first, types other than lists can have maps. So here's a map on options, right? You may or may not have a value of type x. Here's a thing you'd like to do that would transform the value from x to y. And you can get an option y one of two ways. Maybe you never had an x, in which case that's just the same as never having a y. Chill. Or maybe you do have an x, but then okay, f can take us across the bridge. That'll take us to y. You could also define one of these for binary trees. Could be a good exercise, though we don't have you do it here. If you want more practice, I think that's a nice way to do it. What follows are some variations on how map works, sort of embellishments to make map a little bit more powerful. So this function option map, let's not get confused, is the notion of mapping on options, right? Optional values. The function map option is works a little differently. Our function f might return a y, it might not. If it returns some y, then okay, great, we'll include it in the list. If it doesn't return any y, if it returns a none, then great, just skip that x, it didn't pass. In a certain sense, you can think of it as a combination between map and filter, sort of doing the work of map and filter at the same time, where rather than returning false, we would return none, and rather than returning true, we return the y we'd like to replace it. Map option combined the ideas of map and filter in one go. So this is one exercise for you to do. This is actual homework, not just like a good practice thing, like writing map for BT. Okay, here's another one, another variation on map, which says, my function f doesn't necessarily return just one y. It can return a whole list of them. So we give some examples here telling you what we expect it to behave as, right? Flat map, so named because it flattens the list y. Says, well, look, if what I return is these three numbers, then I should get 111, 555, 444 out of applying this to just the list 154. Okay, and a last optional assignment. So you do not have to do this, and we are not going to grade it, but this is another good practice thing that we've gone to the trouble of actually filling out the general idea for you. You can use flat map to implement map option. That is to say, flat map in some sense is more general than map option. If you've got flat map, you can implement map option. So we ask you to do that here. You shouldn't have to use any recursive code or anything, no fixed points, no let fix, nothing like that. You should just be able to take this f and craft it into something else that implements map option. I should add, okay, flat map also generalizes map, just like map option does. If you have map option or you have flat map, you can use that function to implement map. And that's another good exercise to play around with. Wow, having trouble talking. Okay, after this, I think we're going to do just two more videos, one on the higher order predicates. You can see the header down there in the next bit of the file, and then another on a case study talking about DNA and amino acid codons. All right, talk to you soon.